Okay, I think it's recording now, correct? Okay. So I'd like to welcome everyone to my talk, and I'd like to thank the Virtual Science Forum for setting this up. So what we'll be talking about today is some work that I've done with both Kevin Bedell and myself. So in this work, the foundation of this work was set up in this new Journal of Physics article that was published earlier in the summer, and the majority of this, the meat of this talk will be from the Journal of Low Temperature Physics paper in 2020. So what I really want to get across in this talk is a story, and the story of basically where this field is now and where it's going. So I'm going to emphasize some of the mathematical derivations, not go too much into math, but more, like I said, emphasize in this narrative. So if you have any questions, just please stop me because I might not see you. Raise your hand. So basically what my talk is about is this intersection of Fermi liquid theory and Luttinger's theorem. And this concerns some of the details in many body systems, but that's really difficult. So let's play Sudoku. So in case you haven't seen it yet, Sudoku is basically a simple game where we have these numbers in a certain grid. And basically how you play the game is you put in a certain number, say like 4, for 4 to be here, and then you can't have 4 in any of this order in this column. And it's going to be a certain configuration that satisfies these Sudoku rules. So we can fill in this, and we see very easily, for example, if I put a 7 here, and there's no other 7 in this row, and there's no other 7 in this column, right? And why this is connected to my talk, you'll see in a second. So this is basically how you play normal Sudoku. But we can, and we don't really see any kind of order here, but we can up the ante and add some more complexity, some more rules into the equation. So this was a generalized Sudoku puzzle, and no numbers have been filled in yet. I'm going to fill them in a second, the numbers you need to solve this puzzle. So this is a puzzle developed by Mitchell Lee, which is a generalization of Sudoku. So basically, normal Sudoku rules apply if I put a chew here and a no chew in this column and no chew in this row. But we also have anti-night Sudoku rules. So anti-night means if I put a chew here, then I can't put a chew here, say, or if I put a chew here, then no chew here. So Knight's move applies. Non-consecutive Sudoku rules apply. So if I have a chew here, I can't put a 3 here or a 3 here. And no chew touching squares horizontally, vertically, or diagonally can have the same number. So this is known as the king's move. So I can't have, if I have a chew here, I also can have a chew here. Okay? So now I'm going to put in the numbers. Now you need to solve this puzzle. So with this 1 and this chew, you can actually solve the entire puzzle, and I believe there's only one solution to it. And what's interesting, so for first of all, notice if I put a 4 here, there is no 4 in a knight's move, there's no 4 in king's move, and normal Sudoku rules, and there's no 3 or 2 or here or here. Now, what's interesting is that if you look closely, you begin to see some patterns. So 4s sort of form a lattice, as well as 9s, as well as pretty much every other number, form this ordered structure. And if you look very closely, you can see that every row sort of repeats itself. 9, 4, 8, 3, 7, 2, 6, 1, 5. 9, 4, 8, 3, 7, 2, 6, 1, 5. 9, 4, 8, 3, 7, 2, 6, 1, 5, and so on. So what's interesting is even in this very, very simple system, if we add a few additional rules, we get in this long-range order. So in physics, when we deal with this long-range order, what's very popular, obviously, now is topological order, right? So this is what the 2016 Nobel Prize was awarded to Thales, Haldane, and Kosterlitz on topological phase transitions. I'm not going to be talking about topological phase transitions or long-range entanglement in this talk. So I'll be talking about more of a traditional view of strongly correlated systems. And to understand where I'm going to go in this talk, what I mean by strongly correlated, we have to understand a little bit about off-diagonal long-range order. So off-diagonal long-range order, now we're going to physics and passing these Sudoku puzzles, is basically if we have the existence of an eigenvalue of the reduced density matrix, which is now the ordered system size n. That is, there's a macroscopically large eigenvalue of rho. And the value then takes on the condensate density in a Bose-Einstein condensation. Now, what I want to bring up is basically these systems, we usually consider them to not have conservation of particle number, right? Instead of Bose-Einstein condensate. So I want to bring to your attention this one quotation by Philip Anderson, which really sets the philosophy of this talk and my research. So let me read it quickly and then I'll explain why it's so important. So long as one is talking about a single isolated superfluid system, like a single hunk of a superconductor or a bucket of a superfluid, then the number of electron pairs is perfectly fixed and a Hamiltonian must commute with the number operator. However, no separate piece of a superfluid system is adequately described by a single state with off-diagonal long-range order. Of course, it is possible to do things properly. We can start from a supermicroscopic system which has definite fixed particle number and which contains every single little piece that I'm going to use in my system, but that is just inconvenient. So when we deal with these, say, superconducting systems or say these Majorana systems, we normally say they don't conserve particle number. However, if we have a hunk of a superconductor or a bucket of a superfluid, and then the electrons aren't going to go anywhere, it just becomes extremely inconvenient to deal with them if we go beyond this mean field approximation, say. So now what I want to talk about is basically systems where we can still have this single particle approximation. I think Schrafer defined it as this. Basically, if we can still say that much like the non-attracting Fermi gas, we can still talk about coherent particles. So you're probably asking yourself right now, why do I want to apply this idea of many-body theory that is inherently inconvenient? So basically what I want to emphasize is that I want to understand something much more complicated. And to do that, we had to focus on the basic sort of fundamental components first. So this is very similar, I feel, to the work of Picasso, where in his philosophy, where before he could really dive into more abstract art, he first had to master the basics. And I think he mastered them when he was only a teenager. So in the same way, before we can really tackle these more complicated systems, we really have to understand, at the end of the day, this idea of single particle approximation. Basically, where a system seems to have still well-defined particle number conservation in a single particle approximation. Now, the first system that was first considered, where we, with the simplest of these many-body systems, we comply this single particle approximation, was superfluid helium, specifically superfluid helium-3. So helium-3 atoms are fermions, so we don't have any Bose-Einstein condensations, and that's easy. And there's no superfluid transition at high temperature. So basically what we want to define first is this borderline simple system, this normal Fermi liquid. So what is basically a Fermi liquid and how does this fit into the philosophy of what I'm talking about? So Landau, who can be seen here in the background, developed Fermi liquid theory in, I believe, the 50s. And once again, it can be summed up with a nice quote. As we basically gradually turn on to interactions between atoms, the classification of the levels remains invariant. That is, now we can describe the system in terms of these elementary excitations or quasiparticles, each of which possesses a finite momentum. They obey Fermi-Dirac statistics, that is, they also obey a Fermi-Dirac distribution or Fermi-Dirac-like distribution, and a number always coincides with the number of particles in a liquid. So unlike Anderson's description of this inconvenient single particle approximation in, say, a system that obeys off-diagonal long-range order, in a Fermi liquid, by definition, the number of quasi-particles always coincides with the number of particles in a liquid. So this obeys a single particle approximation. Now, the Fermi liquid literature is very rich and complex, but I want to emphasize just a few basic ideas first before we go into the rest of this talk. So there's a phenomenological approach to Fermi liquid theory and a microscopic approach. The phenomenological approach is basically we take the interacting free energy, we expand it in terms of basically the change of distribution from the equilibrium. This is denoted by this delta n. So basically, the magic of Fermi liquid theory is that all interaction is based around this interaction parameter F, this Landau parameter, which is the second functional derivative of quasiparticle energy. Now, we can split this Landau parameter in terms of the symmetric component and anti-symmetric component, and then expand in terms of Legendre polynomials. And then at the end of the day, what we get is something called the parametric instability condition. So the instability condition basically tells me, okay, this condition is what has to be obeyed if Fermi liquid theory is to be applicable. So for example, if I look at the L equals 0 channel, which basically corresponds to this breathing mode at the Fermi surface, and then 1 plus F naught and lambda is S or A here has to be larger than or equal to 0. If this is broken, then we get a negative compressibility and the Fermi liquid theory breaks down, which also means we have a breakdown in a single particle approximation. Now things become a little bit more complicated. We can't describe things very well in terms of something that looks like a single particle. And then also from this formalism, we can also describe the collective modes in this material. This is from this Landau kinetic equation. And we can ultimately see, say, 0 temperature, 0 sound, or hydrodynamic first sound. So this is the phenomenological approach. Well, when and where Fermi liquid theory breaks down, even beyond its parametric instability condition, was expanded upon in the 60s and 70s. And much in this work is talked about in the book by Abrikosov, Gorkov, and Zaleshinsky, which is shown here in the background. And the microscopic foundations of Fermi liquid theory, and ultimately pretty much a lot of non-Fermi liquids, pretty much all non-Fermi liquids, is from this Green's function approach, this diagrammatic approach. So the non-interacting Green's function is given above here. And the magic now is when we talk about the interacting Green's function, G, we can expand it in terms of these Hartree and Fock terms of the diagrammatic expansion. And if we ignore, say, the Hartree term, just consider these rainbow Fock terms, we can combine all of the Fock terms and choose some general self-energy given here. And then we can approximate it as something that looks pretty much identical to the non-interacting Green's function, but now modified by a quasiparticle weight. So this is the part that looks like a single particle, all Green's function, now with a new weight attached to it. And this is the incoherent part, which is something that doesn't look like quasiparticles. And the quasiparticle weight itself can basically be thought of as the discontinuity in the fermionic distribution function at the Fermi energy. And I'll show you a graph in a second. And it's this deep connections to the self-energy, and this will become very important later on. And where we measure it basically in the lab is by looking at a spectral function, which is connected to the imaginary part of the self-energy, which is itself connected to the inverse lifetime of the quasiparticle. Now, we can cement this more with experiment. So an experimental procedure, and this is a diagram taken by in this paper given down here. And basically what we see is that if we were to do Enkel-Lazar photoemission spectroscopy on a system, that is ARPES, on a non-interacting Fermi system, basically the spectral function, it measures the spectral function, what it yields is these delta function peaks. So basically that tells me I have these non-interacting well-defined particles. In a Fermi liquid, we should also have these well-defined peaks, but then also this incoherent part. So when we have these delta function peaks disappear, then we no longer have a well-defined quasiparticle. And we can see here what I was talking to you about before, how this quasiparticle weight is connected to the discontinuity of the distribution function of Fermi energy. So when Z goes to 0, Fermi liquid theory breaks down. When the lifetime goes to 0, so inverse lifetime goes to infinity, and then basically we lose this delta function peak, and Fermi liquid theory breaks down. So it would seem as if we have a well-defined idea of where Fermi liquid theory breaks down and where it doesn't, but this really isn't the whole story. So some materials that have caused some issues recently is the high temperature phases of the cuprates. So of the cuprate superconductors. So these are high temperature superconductors, which basically have these exotic phases above the transition temperature. So the dotted line here, so this is a diagram taken by this nice paper from Jan Janin, and this dotted line basically just tells me where the order or the fluctuations become apparent, and they're not important for what I want to emphasize. What is important is that you notice that if I look at this as a function of hole doping versus temperature, we have a strange metal and a pseudogap phase. So the strange metal phase is basically doesn't have a it basically has 0 quasi-particle weight, but it's not superconducting. And the pseudogap phase is even more interesting because it seems to be defined by what's known as a small Fermi surface, or in many cases, a discontinuous Fermi surface with Fermi arcs. So there have been a lot of debate recently about what features of, say, strange metal pseudogap shares with a Fermi liquid, whether it can be modeled coherently in terms of a similar mechanism. And what I want to ask in this talk is what's required for a Landau quasiparticle to exist. And this will be primarily given in terms of the formalism of Luttinger's theorem. So first I'll start with an introduction to Luttinger's theorem, and then Luttinger's theorem beyond Fermi liquids beyond Luttinger's theorem in future directions. But first, if you have any questions, please ask. So maybe I'll stop for a few seconds.
Yeah, I have a question.
Yeah.
So you said that, yeah, so at some moment Fermi liquid theory breaks down when the lifetime of a quasiparticle is too small, or the quasiparticle residue is too small. But I mean, it's a continuous process, right? So when do we say that we still have a quasiparticle? When do we say that we don't anymore? I mean, how do we, what are the typical values of the quasiparticle lifetime should be so that we can still treat? Yeah.
I mean, basically, I wouldn't, and so that's an interesting point. It just sometimes it isn't actually a continuous transition. There's something in two-dimensional Fermi liquids called the orthogonal catastrophe, where basically at some point for some attraction, Z goes to 0, and a quasiparticle lifetime goes to 0. So in many of these extreme cases, it isn't, say, a continuous transition where the lifetime is, say, very large and then it gradually gets smaller. It's just snaps down to 0. In general, I would say that it's not a very clear answer. Generally, when a quasiparticle lifetime gets smaller, it just becomes harder and harder for Fermi liquid theory to be described. But I would say the most interesting cases I want to consider are those systems where Fermi liquid theory is just hopeless, where it just goes down to 0 completely. And also, there's another interesting point where there's something called a marginal Fermi liquid, right? Where basically the quasiparticle weight is just barely 0. So the self-energy goes as log of the temperature or log of the energy. So and there's even been debate of whether or not that's a Fermi liquid or not. So, I mean, and it's not a clear-cut question I would feel to not answer beyond, say, the trivial case of helium-3, where we know it's definitely a Fermi liquid.
So basically, the smaller the lifetime of the quasiparticle, the harder it is to treat the problems perturbatively, right?
Yes, so the harder it is and the more controversial it is.
It does not converge? It converges worse, or what do you mean by harder?
Oh, so I mean basically, you might see some non-quasiparticle contributions, right? So there's some work by Schmally and Wuffel who've shown that there's non-quasiparticle contributions to the vertex, and this ultimately will lead to the destruction of Fermi liquid theory. So basically, I mean, if you have more of these non-quasiparticle contributions, then indirectly, Fermi liquid theory will become harder and harder to, it will become more difficult to describe the system, and more controversial to describe the system in terms of Fermi liquid theory.
Okay, thank you.
Any other questions? Okay. So now let's go to introduction to Luttinger's theorem. So Luttinger's theorem was first developed by Joachim Luttinger, who is shown here on the right. And once again, it's nicely summed up by this quote from his paper. So it's shown that certain analytical properties of the propagators of many fermion systems, these Green's functions, lead rigorously to a sharp discontinuity of the momentum distribution at absolute 0. So what I showed you before. This discontinuity in the momentum distribution is used to define a Fermi surface for a system interacting fermions. It is shown the volume of the surface in momentum space is unaffected by the interaction. So basically, this is Luttinger's theorem in a nutshell. As I turn on some interaction, the Fermi surface will remain the same. It won't change in volume. And it's a direct connection between the non-interacting particle density and the volume of the Fermi surface itself. So this seems like a very simple argument, but actually it's extremely controversial, and 60 years after its initial development, it's still being debated to this day. So let's try and understand this a little bit better. So the first thing you have to understand is in this deep connection with Fermi Luttinger's theorem and the phase derivative of Green's function. So we can relate the non-interacting density of the particles to the Green's function. It's just a phase space integral. And then basically we can just change the way, we can just do some algebraic manipulation to the Green's function and put in this form. So this basically simplifies it actually, because I can split into two integrals, this integral and this integral that we had to consider to look at Luttinger's theorem. So first I want to look at this integral. And I'm going to do the next integral on the next slide. So it can be shown that this integral can basically reduces to a k-space integral over the phase of the retarded Green's function, the difference of phases at omega equals 0 and omega equals -infinity. So from the spectral decomposition to Green's function on whether or not it's a Fermi liquid or not, at omega, as omega goes to infinity, the Green's function will go as 1 over omega. This is a real value, which means that the imaginary part of the Green's function should go to 0 faster than the real part as omega goes to infinity. So that tells me that from the tangent of phi related to the imaginary and real parts of the Green's function, at phi at -infinity should be pi. So that solves an n. Now the other one is a little bit more subtle. So here's we have to basically bring in some formalism for Fermi liquid theory. So from a calculation of in its lifetime, we can show that for Fermi liquid, the imaginary part of the self-energy should go as omega squared. Now from the Kramer-Sonkono relation, the real part should go as omega, because the imaginary part of the self-energy goes to 0 faster as omega goes to 0 than the real part, phi of 0 equals 0. So once again, I'm going to show in a few minutes a summary slide. But basically, phi at -infinity equals pi due to basically causality arguments, and phi at 0 equals 0 due to the structure of Fermi liquid theory. And this basically leads to an extreme simplification. But wait, we just shown that the density is equal to the volume of the Fermi surface, which is Luttinger's theorem. And we didn't deal with this next component, this next integral. So for Luttinger's theorem should be valid, this next integral has to be 0. So this is where we go into what's known as the Luttinger-Ward functional. So this was the integral we showed before, and it has to be 0 for Luttinger's theorem to be applicable. I can just redefine it as that. And what this tells me is that I can write the self-energy, if this integral is 0, the self-energy can be written as an exact differential of this functional phi. This is known as the Luttinger-Ward functional. And basically, to go into details, it's the sum of all bold closed two-particle irreducible diagrams. And it has a deep connection to even statistical mechanics, because we can connect basically the free energy to phi. And this is known as a phi derivative of phi. And this is known as a phi derivable theory. Once again, this is talk about Abrikosov, Gorkov, and Shalansky. So what I want to emphasize here is that if you can write the self-energy as in terms of this Luttinger-Ward functional, then this next part of the integral disappears. So a Luttinger-Ward functional has to exist for Luttinger's theorem to be applicable. Okay, so let's go over this again, because this is very important. We can write the density, the fermionic density, in terms of the Green's function, and it splits up in two integrals. One integral can be simplified in terms of the phase of the retarded Green's function. And by invoking Fermi liquid theory, basically the imaginary part of self-energy goes as omega squared, and the real part goes as omega, phi of 0 equals 0. And then the boring part is phi at -infinity equals pi, which is just due to causality. And now the other interesting part is that we had to have a Luttinger-Ward functional exist. And there's another detail. The Green's function has to change sign at the Fermi energy. But basically, if we put all of this together, basically the Green's function has to change sign because we had to have something like a Fermi surface, right? So if we have a Fermi surface and we have all of these things together, then Luttinger's theorem applies, and the volume of the Fermi surface remains invariant to any interaction. So on any questions at this moment?
Yeah, maybe one question, because you
Sure.
say it this will apply under any form of interaction, but the interactions are going to change the self-energy. So it really rests on whether the low energy extrapolation remains omega squared.
Yes, that's
not necessarily true.
Yes, so and that will be the focus point of the next, that pretty much the rest of my talk. So when Luttinger first introduced this, so when Luttinger first introduced this was for any interaction, but maybe I'll give a little spoiler. So obviously, it's going to break down for if I have a gap, right? And then if I have a gap, then basically the form of self-energy will have a much different frequency dependence, and Fermi liquid theory just breaks down. I mean, Luttinger's theorem breaks down. Also in these systems, Luttinger-Ward,
for marginal Fermi liquids, Fermi liquids, it would break down as well, right?
Yeah, so marginal Fermi liquids, so marginal Fermi liquids will break down. It basically, wherever I have no Luttinger-Ward functional as well, it will break down. And I strongly believe that for the pseudogap phase, as I'll show later, it will break down. So, however, there are some non-trivial cases where we don't have a Fermi surface, but it remains. So this is what I want to talk about now. And that's a nice segue. Let's learn any more questions. Okay. Luttinger's theorem beyond Fermi liquids. So now Luttinger's theorem is a very, very deep theorem. And like I said before, it's very controversial where it applies and where it doesn't apply. So I really like this. Once again, another quote from this paper, and there's a deep connection with Luttinger's theorem and ADS-CFT, which I'm not going to go into. But I really like this quote from this paper. Now, in Fermi liquid theory, a quasi-particle spectrum is only dependent upon excitations at the Fermi surface, right? However, the non-trivial point of Luttinger's theorem is that it relates the spectrum not only near the Fermi surface, but also deep inside the Fermi surface to the charge density. So Luttinger's Fermi liquid theory just tells me what's going on near the Fermi surface. Luttinger's theorem tells me something that goes on in the whole Fermi surface itself. It tells me something that goes on deep inside the Fermi surface, where the quasi-particle picture breaks down. Now, naively, one would think, well, if a system-based Luttinger's theorem, then it probably has to be a Fermi liquid, right? Well, that's not necessarily true. Now, one of the major cases when this was shown was in a one-dimensional Luttinger liquid. So in a Luttinger liquid, basically a one-dimensional interacting fermionic system, Fermi liquid theory breaks down. Fermi liquid theory works fine in 3D. 2D, it's a little controversial in some cases. 1D, it's hopeless. It's because we don't have any well-defined quasi-particle, as we can see from this plot taken from this paper by Voigt. So Fermi liquid theory is hopeless. Now, what's interesting now is that in the early 90s, or late 90s, sorry, a separate work by Bedell and Blackwave and another group led by Shirkawa and Affleck shown that Luttinger's theorem actually exists in a 1D Luttinger liquid by basically generalizing the Fermi surface and defining once again at the Fermi points is where the Green's function changes sign, they were able to show that Luttinger's theorem is applicable. So Fermi liquid theory breaks down immensely, but we can still apply Luttinger's theorem. Now, this was expanded upon a little bit later by this work by Zaleshinsky. And once again, I really like this quote: the proper tool to use for modern insulators and non-Fermi liquids is the so-called Luttinger's theorem. Once again, as I said, because it goes beyond the quasi-particle picture. However, the contents of the theorem are so densely clouded by folklore that it is sensible to begin with a statement what it is when we say Luttinger's theorem. So Zaleshinsky, one of the main people who've really pushed this, some of the foundations of this field, and one of the authors on a book I mentioned before, Aprokazov work of Zaleshinsky, even says Luttinger's theorem, the main tool is clouded in folklore. So in his paper, what he showed was that Luttinger's theorem is applicable for systems with Luttinger surfaces. So let's try to organize ourselves here. There's Luttinger's theorem, which I showed before, Luttinger liquids, which are one-dimensional fermionic interacting fermionic systems, and a Luttinger surface. So a Luttinger surface is a manifold of where the Green's function is 0. So a Fermi surface is where the inverse Green's function is 0. A Luttinger surface is where the Green's function is 0 itself. So what Zaleshinsky said is, well, Luttinger's theorem will still be applicable if G equals 0. And then this was a very controversial statement. And since then, people like Zvelak and Philip Phillips have gone on to say, well, it depends, basically. In many cases, we can have a Luttinger surface, and Luttinger's theorem just completely breaks down. So what I want to talk about now is how can we correctly generalize the Fermi surface to basically push Luttinger's theorem beyond just generic Fermi surfaces for dimensions larger than 1. So we can do this by pushing this theory of these two fellows, Kanoff and Bain, and ask ourselves, what is a Fermi surface? So recall that a Fermi surface is basically defined in an interacting system by this non-zero quasi-particle weight for Fermi liquid. And this can be represented in terms of the self-energy, right? Now, what was the magic that Bedell and Blackwave did in the 90s? Basically, they redefined what we mean by a Fermi surface in a one-dimensional system. So now we define it as where some mth derivative of the distribution function diverges. So for a Fermi liquid, what will happen? M equals 1, the first order derivative will diverge. However, for a Luttinger liquid, even though I have a smooth distribution function, no quasi-particle weight, the second derivative will diverge. Or yes, I believe it's actually for the Luttinger liquid, the first derivative still diverges. So that's also m equals 1. So by redefining a generalized Fermi surface beyond just some generic quasi-particle weight, defining in this way, we were then able to prove Luttinger's theorem for Luttinger liquid. So now, once again, I want to redefine the Fermi surface as well. And in my paper, basically shown here, it basically is equivalent to this. And that's from this kind of Bain functional. So in many-body physics, we can define some generating functional in terms of this partition function, basically. And here, z tilde is here. Z tilde is an interaction-dependent constant. And before, J and K were just some sources for the field. And for a many-body system, what I want to emphasize is that the generating function can be expressed in this form. So this is self-ended Luttinger-Ward functional. This is self-energy in Green's function. It's just trace over spin indices. So what's interesting is that as I go closer to the Fermi surface, I'm going to assume that this is well defined. And this is basically trivial. So all the magic is contained within here. So now I can map, and this basically becomes a phase. The interaction contributes a phase to the many-body generating functional. And this can be mapped to a winding number. So the winding number basically tells me, okay, if I have a 0 of inverse G, if I have a Fermi surface itself, there's 0 inverse G, then I will have some, this will be some number, right? So this basically tells me that if I have a Fermi surface, I have a non-zero winding number. But wait, I have basically in terms of this generating function, this was in terms of log of negative G, and it can actually be easily shown that this also similarly applies. So I'll also have a non-zero winding number if I have a Luttinger surface, 0 of G itself. So basically, I'll have a non-zero winding number for both Fermi and Luttinger surfaces. Now, this isn't that controversial in a sense, and has already been introduced in this idea of a winding number in terms of a Green's function. This was introduced by Volovec in 1991. And here we can see a little better definition of this, the path to calculate this winding number. And here's a generic Fermi surface in 2 dimensions. Now, what I want to emphasize here is that we can connect this Volovec's original idea of this topological invariant, this winding number, back to microscopic details when it's calculation. Basically, it's deeply connected to a phase of the many-body generating functional. The other thing I want to emphasize too is that we will also have a non-zero winding number for a Luttinger surface. Now, I'm not saying that every single instance of a Luttinger surface will have a non-zero winding number. And this implies that I have a well-defined Luttinger-Ward functional, which is not the case in a superconductor. But what it says is that a Luttinger surface can yield a non-zero winding number. So why do we care? Why is this important? Well, we have to go to an idea in high energy physics called an anomaly. And this is basically what I want to emphasize here is that we can view the Fermi surface as an anomaly. So an anomaly is defined as a symmetry of the classical Lagrangian, which is lost in the process of quantization. Much in the same way as before, when we can talk about this determinant of the Dirac operator. Once again, this leads to some phase in terms of this little w. And this little w can then be expressed as, once again, a winding number, which defines a topological index. And then from something known as the Taylor-Singer index theorem, we can connect the topological index to the analytical index. And what does that mean in terms of physics? It means that I have some non-zero chiral modes if I want some non-zero winding number. So what this tells me is that if I have a non-zero winding number, then I will have some breaking of chiral symmetry at the Fermi surface. And what it tells me is that both Luttinger and Fermi surfaces can be mutually defined as lower dimensional manifolds of some gapless chiral excitations. Now, once again, this doesn't say that every single Luttinger surface will have this lower dimensional manifold of chiral excitations. It means that it can happen. The other thing, too, is that, once again, this is not natural controversial of a statement. Zwingli actually proposed a few years ago that a Fermi surface can be viewed as a collection of 1 plus in 2D as a 1 plus 1D chiral conformal field theories. And some other discussions have talked about a finite density of states leading to a breaking of chiral symmetry. What it shows is that we can have this lower dimensional manifold of gapless chiral excitations for a Luttinger surface in some system. What system? Personally, I think the half-filled Hubbard model on a triangular lattice might be a case. It's a case where basically we don't have a well-defined Fermi liquid, but it's gapless. So that might be an example system, but more work has to be done. So basically, what did I do? I generalized the Fermi surface to include a feature that's shared with both the conventional Fermi surfaces and Luttinger surfaces. So why do I care? Why do we care? Why do we care? How does this connect to Luttinger's theorem? So both Fermi surfaces and Luttinger surfaces can be defined as a lower dimensional manifold of gapless chiral excitations. This defines a generalized Fermi surface. Now, I'm not going to show it here, but from Kramer's conic relations, there was a question before about some general self-energy, form of the self-energy, right? So I consider self-energy going as omega to alpha, where alpha is larger than 1. If alpha is between 0 and 1, the condition on the phase phi 0 equals 0 is violated. If alpha is smaller than 0, the Luttinger-Ward functional is ill-defined. So basically, we had to be very careful when it's forming a self-energy. This form, I believe, is connected to the pseudogap phase. So degeneration of fermions, and basically in this interesting Fermi pseudogap phase, which we still know very little about, and alpha smaller than 0 is basically gapped. I'm pretty confident that this is gapped, and like I said, I'm confident that this is pseudogap, and that's a little bit more controversial. Yeah, so that's just what I said. Now, the generalized Fermi surface, remember, disappears when Luttinger's theorem breaks down, right? So putting these two calculations or two ideas together, what we can conclude is that the sole necessary and sufficient condition for the validity of Luttinger's theorem is existence in this generalized Fermi surface. So one point I want to emphasize too is, well, where do we get Luttinger surfaces then? Remember how I defined the form of the quasiparticle weight? Basically, if I have, or the form of the Green's function, if I want a Luttinger surface, I need to have a diverging self-energy. But if I constrain my self-energy like this, how does it diverge? Well, it has to diverge in a k-dependence. If it diverges in a k-dependence rather than an omega dependence, so now I call it a quasi-local model, and then you can have a Luttinger surface and still obey Luttinger's theorem beyond the Luttinger liquid. So the whole point in this part of the talk I want you to take away from is that Luttinger's theorem can exist if we have a generalized Fermi surface that includes both normal Fermi surfaces and Luttinger surfaces. Now, before I go to the next part of my talk, if anybody has any questions.
Yeah, actually, just to make sure that I'm still following. So if I look at the second bullet point of your list here, then I would probably agree that there is experimental evidence that in the pseudogap phase, alpha is smaller than 1. But this is measured at the nodal point of the cuprate Fermi surface, which is also the point which is not gapped. So you made a statement about the quasi-local model, or in other words, a non-local model. So I missed the point how these two things connect, because the point of the Fermi surface, which remains in the pseudogap phase, shows an alpha smaller than 1, yet it is ungapped. So I missed that point.
That's an excellent point. So this alpha between 0 and 1, I agree with you. I don't believe it should be gapped. What is happening in between there, I really don't know. So I think there's a deep connection between maybe I think more work has to be done on Fermi arcs in this context, as well as in general what's happening for alpha between 0 and 1. I don't believe it's gapped, but if that is the case, then what I'm saying is that the phase in this condition, phi 0 equals 0, will break down. So basically, the imaginary part of self-energy and the real part of self-energy will both go to 0 at the same rate. So I still have a well-defined Luttinger-Ward functional. So I don't believe it's going to be gapped. It's going to break down due to some other reason. However, I do believe that my original conditions on this generalized Fermi surface break down, but not because it's gapped. And what is going on in the pseudogap phase itself, I really am not sure. And there's some interesting work on cellular DMFT from Secure Sakai, and it seems to suggest that Luttinger's theorem is violated in the pseudogap phase of the Hubbard model. So that's one avenue of looking at it. And there's also another avenue of looking at it in like a generalized Hubbard model analytically. But what's going on specifically in this range, I think more work has to be done. But it's not because it's gapped. Any other questions? Okay. Now,
sorry,
yeah.
I have a simple question, but I think it would help me understand. So you're talking about Luttinger surface as having gapless chiral excitations, but in which sense does a linear Green's function have excitations? So is there a way to understand this somehow intuitively? So we're talking about the proximity of a 0 of a Green's function. What does it mean?
Well, in general, we can define, say, a Fermi surface as some 0 of the inverse Green's function, right? And then and this basically defines a normal Fermi surface where I have where I can find these normal Landau quasiparticles. So what I'm saying is that in a certain system, we might also be able to have something similar. We might also be able to have something that looks like, well, I don't want to say like a quasiparticle because it's not a quasiparticle, but something that might be able to look like something we can push towards a quasiparticle-like excitation in a system that has a 0 to Green's function that still remains gapless, but still has something that looks like a collective excitation. That is like a what I mean, like I said, it's going back to this idea of this Hubbard model on the triangular lattice, where we don't have a gap, it's still gapless, but Fermi liquid theory breaks down. And so that's what I'm really trying to look at in this context. Just basically a generalized Fermi surface.
All right, thanks.
Any other questions? And like I said, to really cement this idea of, what's going on? How can we define these collective excitations? That's a subject of future work. I think it's deeply connected to the idea of conformal field theory, like Swingle talked about, but more work has to be done. on this. I think it's some limiting case of a quasiparticle, of a Landau quasiparticle. And it's even been work, I think, within 2 weeks at POB has shown that Fermi liquid theory can exist beyond breakdown, beyond the existence of a conventional Landau quasiparticle. So it might be connected to that as well. So maybe let me go. So basically, the first part in this talk cements the idea, okay, Luttinger's theorem can exist beyond a Fermi liquid. And I want to talk about Fermi liquids beyond Luttinger's theorem. So this is deeply connected to this idea of unparticles. So unparticles were first defined by Howard Georgi in, I think, the early 2000s or late 90s. And basically what unparticle is a physical particle-like system, particle-like structure that has a finite mass, but it's still conformally invariant. So it's still scale invariant. So it's basically a step beyond the standard model, and it can't be described by a normal standard model of physics. And what Philip Phillips and company first showed was that, well, maybe we could have something like this in a condensed matter sense, right? So can we actually have an unfermi liquid? Now, his quote was basically, if the Luttinger count fails to yield the charge density, there are charge degrees of freedom left over which have no interpretation in terms of the single particle approximation I mentioned before, that is particles. So if Luttinger's theorem breaks down, like I said, Luttinger's theorem is a very robust definition of a single particle approximation. This Anderson's bucket, we could call it. But back to this idea of Anderson's bucket of a superfluid. But when Luttinger's theorem breaks down, well, what happened to those collective degrees of freedom? Well, they might be an unparticle. They might be something that we can redefine in terms of our standard model of physics. So once again, this idea was spearheaded by Philip Phillips, and there's a huge amount of literature on this by Phillips and company. And I suggest you go back and read some of these amazing papers. But I want you to take away a few major points. So the chemical potential in these systems, i.e. the Luttinger surface, can be placed anywhere we like in a Mott gap. So if we have a gap system, like I said, the Luttinger surface doesn't tell us that Luttinger's theorem will be obeyed. It just tells us that there can exist some system out there where I have a Luttinger surface and Luttinger's theorem is obeyed. So if we do have a gap, then why does Luttinger's theorem fail intuitively? Well, it's because I can place the chemical potential, the Fermi energy, anywhere I like in a gap. So if I put it here, Luttinger's theorem is obeyed, but if I put it here, when I have a small Fermi surface, so it breaks down. So that's an intuitive way that Phillips really spearheaded, and that why Zaleshinsky's original argument that any Luttinger surface can obey Luttinger's theorem breaks down. The other thing is that a divergence of energy implies an ill-defined Luttinger-Ward functional. So once again, it's connected to the gap phase. If I have some divergence of energy in terms of k-dependence, it won't affect this Luttinger-Ward functional. Now, finally, what Phillips showed was that if I have a Green's function going as some power, Luttinger's theorem fails. Assuming that the imaginary part of Green's function is not zero or particle symmetry is absent. So this is very important because that means that this is basically the form of the propagator that Howard Georgi proposed for the unparticle system. So if we take this unparticle-like propagator and it has this power law, then Luttinger's theorem fails. Well, not really. Phillips later showed that there are special cases where both of these cases, the imaginary part of Green's function and particle symmetry is absent, but Luttinger's theorem still works. If one is between alpha is between 1 and 2, Luttinger's theorem is fine. Obviously, I'm going to have a power law like Green's function for Luttinger liquid, but Luttinger's theorem still works. So what I want to talk about now is whether or not Fermi liquid theory can work for this power law Green's function. So you might say, well, Luttinger's theorem fails, so Fermi liquid theory should fail too. But it's a little bit more complicated than that. So in the same way that Luttinger's theorem can be applicable without a Fermi liquid, it can be shown that Fermi liquid theory can be applicable without Luttinger's theorem. So in 2012, Zhao and Wen and company basically shown that the pseudogap phase of the cuprates could be modeled as a Luttinger volume violating Fermi liquid in this material. So the pseudogap phase above T seen as optimal material has well-defined quasiparticles in the nodal region, resembling the feature of a standard Landau-Fermi liquid. However, it has small Fermi particles without the translational symmetry breaking, which violates the Luttinger's theorem explicitly. So something looks like a Fermi liquid, but small Fermi surface, so no Luttinger's theorem. This has also been shown in numerous other materials, and there are some citations in the paper on Journal Low Temperature Physics I have. And it's also been worked by Sachdev, and it has shown that we can have a fractalized Fermi liquid phase that has a well-defined discontinuity at the Fermi energy, but a small Fermi surface. So something looks like a Fermi liquid, but there's no we can apply Luttinger's theorem to it. So let's try to extend this to the power law Green's functions. I think I'm beginning to run out of time, so maybe I'll try to emphasize the main points. So quasiparticles and non-trivial power, I'm going to consider a little bit different form than what Phillips considered. So I can consider 1 plus chi, or Cassi. So when Cassi equals 0, then I call it trivial power, and we just have our normal Green's function. I can rewrite this as just rewriting it as some Taylor expansion, and then we can simplify it and calculate the spectral weight. This is given here for convenience. And what do we get when the dust settles? We get basically the spectral weight in terms of these parameters here. A of 0 is the spectral weight for trivial power. Cassi is the power. Phi naught is the phase of retarded Green's function of trivial power. X is just omega subtract Cassi. Cassi is energy with respect to the chemical potential. This is the imaginary part of self-energy, and the real part, and this is a lifetime. Now, what I want you to show here is that now we have a new definition of this quasiparticle weight. So the quasiparticle weight now, this generalized quasiparticle weight, can then be represented as the quasiparticle weight at trivial power raised to 1 plus Cassi times cosine subtract cotangent sine, where now we have a strict dependence upon the trivial power and the power itself, Cassi. So what I'm going to show you in the next plot is a plot of the generalized quasiparticle weight at non-trivial power divided by CK1 plus Cassi as a density plot. So what is this showing? This is showing the density plot of the renormalized generalized quasiparticle weight. Phi naught at omega equals 0 is shown on this axis, and the power is shown here. The black is where the quasiparticle weight is negative, so Fermi liquid theory is hopeless. The white is where z tilde over z1 plus chi is larger than 1, so it's questionable if it can be applied, and z itself has to be pretty small. However, where you see color is where Fermi liquid theory is quite robust, even at non-zero power. So you see here, 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 I can have some quasiparticle weight between 0 and 1, and some non-trivial power and some non-trivial Phi naught. So Fermi liquid theory can still, or it's very hopeful that Fermi liquid theory can still be applied in these systems. Okay. Now, what you'll probably learn from the previous slides is that, well, if I deviate from this line, the Luttinger's theorem will probably fail as well, right? So let's go step back a step and look at Luttinger's theorem for its non-trivial power. So once again, we can define in terms of this, Luttinger's theorem has to be applicable if tangent Phi naught equals tangent Phi negative infinity equals 0. The causality argument is going to be applied in this case as well. So I'm just looking at the phase. And this is really the important thing I'm looking at. And we can relate the phase of the retarded Green's function on trivial power to the phase at trivial power through this relation. Once again, I'm not going to show you the math, it's given in the paper. And then the conditions of Luttinger's theorem are much more complicated for non-trivial power. So I'm just going to flash this quick and show you the plots, which are a little bit more illuminating. So it's phi is equal to 0 if this is 0, constant if this is the case, infinity if this condition is satisfied. So this is basically showed through these plots. So let me take 1 or 2 minutes to explain this. Let's focus on A now. This is the case when Phi naught is 0 equals 0. So the phase of the retarded Green's function at trivial power is 0. It's vanished. And basically, when this black line crosses 0, that means Luttinger's theorem is applicable. And this line, the colored line, is a quasiparticle weight, the normalized quasiparticle weight. What do we see? At trivial power, this is just a normal Fermi liquid case, Luttinger's theorem will be applied, and we have some non-zero quasiparticle weight. Everything's fine. However, as we deviate further, well, we don't have a 0 in its function, as I said before, so Luttinger's theorem is inapplicable, but I still have at a 0, a non-zero quasiparticle weight. When a quasiparticle weight goes to 0, Luttinger's theorem then is applicable. Now, and then later on, the quasiparticle weight remains negative, so Fermi liquid theory breaks down. But Luttinger's theorem can still be applicable. The case B is where phi naught 0 is equal to some constant. I just said just some constant here. If I said it's something else, it just stretches the diagram a little bit. What do we see? Non-zero quasiparticle weight. That mean, and then it goes to 0 when Luttinger's theorem could be applied. Luttinger's theorem could be applied with 0 quasiparticle weight, and so on. In this case, you also see similar behavior, but and this is more of a mathematical curiosity, and this is for phi naught 0 equals pi over 2. It violates causality. So this is just for mathematical completeness. Focus on these two plots. Now I want you to show what you should take away from this is that in these systems to the pseudogap phase, and they seem to imply that Luttinger's theorem is incompatible with Fermi liquid theory. What I'm showing is that this seems to be a little bit more universal. If I have some non-trivial phase of the Green's function, then except for trivial power, we will always have Fermi liquid theory be incompatible with Luttinger's theorem. So basically, no matter what, for any non-trivial power, the Green's function, we will always have Luttinger's theorem and Fermi liquid theory will never be compatible with each other. So before I go into the conclusions, any questions on these two plots? Okay. So let me talk about some future directions. So what do we find? Fermi liquid theory is a powerful technique in many body fermionic systems, but it can easily break down. Luttinger's theorem is a more robust analytical technique to understand many body fermionic state, but it is significantly more difficult to understand. And as you've probably seen by now, 60 years later, and people are still arguing about it. Whereas a Fermi liquid requires a Fermi surface, the validity of Luttinger's theorem requires a generalized Fermi surface, that is, in this general lower dimensional manifold of gapless chiral excitations. In the presence of a parallel scaling of Green's function, where people suggested it seems to be like unparticle-like physics, Fermi liquid theory and Luttinger's theorem are only compatible at trivial power with the Green's function. Now, so these are the two main results. So what is now left to do? Well, there's actually quite a lot to do. Can we generalize the Landau quasiparticle paradigm to systems that support a Luttinger surface? So, like I said, this might have deep connections to conformal field theory, and I'm looking at that a little bit now, and I wish I could tell you more, but I can't. If we could generalize this means that we're basically, I mean, Anderson wrote this paper about Fermi surfaces without Fermi liquids. So can we have a Fermi liquid without a Fermi surface? Can Luttinger's theorem survive in a system that supports certain Fermi arcs? And that's something to explore as well. Does divergent k-dependence of self-energy imply fixing at a chemical potential? Remember what I talked to you about Phillips' idea? We have a gap, and then the chemical potential can be put anywhere we want. So Luttinger's theorem is violated. If we have a divergent k-dependence, well, then I've shown that Luttinger's theorem is still applicable. So if we have a divergent k-dependence, this is then fixed to form the chemical potential. Can we show this in a specific model? Some generalization of the Hubbard model, maybe? Does the favorite Luttinger's theorem apply off diagonal long range order? That's something very interesting to look at. And then how does the Fermi liquid die at quantum criticality? And there's been exciting work a few years ago by Wuerffel that's looked at how a Fermi liquid could die or survive in the presence of some non-trivial quantum critical scaling. So I can have some non-trivial value of the dynamical scaling order parameter, and then Fermi liquid theory can still be applicable. So can we push this further? How far can we push this? So when will Fermi liquid theory die? So needs to some of the questions we could explore, and I would also be interested in looking at, like I said before about the work of Secure Sakai, trying to push this further numerically to try and see where's a system that, or specifically that has a Luttinger surface and obeys Luttinger's theorem beyond the Luttinger liquid. And that's the end of my talk. Thank you.
I turned my audio on for that because it's nicer than these hands. Can I ask a question about the last part? I
Sure.
was still absorbing information, so I wasn't that fast. Can you go back to the plots, last plots that you showed? Just, yeah, those. So if I look at panel A, I understand why you say only for trivial exponents, EA eta being 0, you can have a Fermi liquid with a Fermi surface. That's the point you're making there, correct?
Yeah, so basically here, trivial power, Luttinger's theorem is obeyed, and it's a normal Fermi liquid.
There is one other thing which seems to work there, and that's a marginal Fermi liquid, right? So for Z equal to 0, which is the marginal case, that seems, and then the interesting thing is that seems to work for any power of eta. So in your last question, you're asking, how does a Fermi liquid die at quantum criticality? I think the answer to that is you get a marginal Fermi liquid. Isn't that so? So in other words, if we combine these two statements, is it then possible that you can have sort of a generalized marginal Fermi liquid where these powers of eta are all cases where you can in principle satisfy also Luttinger's theorem?
So that's a very good point. So let me go into the structure of the self-energy. So in the original paper that I wrote with Bedell on Luttinger's theorem, I only considered power law forms of the self-energy. Well, power law forms away from the linear case, so I didn't have a marginal Fermi liquid. In terms of this case, so I mean, if I have a very strongly interacting system, the power, so it might be interesting to look at, for example, if I take a very strongly interacting system, the power of the Green's function would be the same as the power of the self-energy. However, there might be some different, so then basically, however, if I don't have a very, very strongly interacting system, it'll be different. So basically what you're saying is that if I consider a marginal Fermi liquid that's described by some power law Green's function. And that has not been explored yet, but that's an interesting point.
Yeah, I don't think that has been explored to the best of my knowledge.
No, I don't think that has been. So when I was talking about before about the quantum criticality, maybe I can go into that a little bit more. Right, and it's been a lot of exciting work about its non-trivial scaling of the charge density. So basically trying to incorporate Landau-Fermi liquid theory. But I haven't thought about it in terms of marginal Fermi liquid under non-trivial power. Yeah, that's a very interesting point. I haven't thought about that yet.
Okay, thanks.
Any other questions?
Not a question, but thanks for the talk. It was really fun.
Thank you for having me.
Yeah, same from me. Thanks a lot for your talk and the time. All right, I have to leave because I have to go. Thanks.
Okay. Bye.